Thanks. So I'd like to begin by thanking the organizers, Ranjini and Mahesh, for inviting me to this really nice school. And thanks to all the students, particularly for enthusiastically attending the third week. Okay, so today I'll be telling you about memory formation in dense granular suspension. So we have the ability to learn and remember specific set of input we learn and we can recall later. And we know that inanimate objects can also do the same. Like we are familiar about magnetic memory, where we can encode information and retrieve it later. So the question is, can disordered soft materials with complex arrangement of constituents can also learn and remember? So apart from the fundamental interest, this question is important in the context of designing smart and adaptive material. The interest is the following, that if we can tune the properties of the material by encoding some memory, then we can use same material again and again by encoding different memories to perform different tasks. Okay, so where to begin? So we know that equilibrium system, by definition, they do not have any memory. So once the system reaches equilibrium, we cannot tell from where the system has evolved to equilibrium. Okay, so the first requirement is it has to be far from equilibrium, out of equilibrium, to encode memory. And so there have been several studies in memory formation in out of equilibrium systems. Some of the examples are this Kovacs effect in glasses, charge density wave conductors, Moulin's effect in field polymeric materials, and memory effect in granular suspension and disordered solids. All are out of equilibrium materials, but these two I am going to discuss in today's talk. And all these papers, there are quite a few papers, and this is a nice review in the Review of Modern Physics in 2019. It summarizes most of the studies. Okay, so it turns out that memory formation in this material is closely in out of equilibrium materials is closely linked to the self organization in the material. So this is just an example. So this is a simulation study. So imagine you have some liquid and you have some particles. The particles are completely athermal. Those are big particles. And the liquid is viscous, and everything I'm going to do is Reynolds number is negligibly small. And so you consider that three particles, like the way it has been shown. So now what I'm going to do, and I'll just apply a shear to the system, okay, slowly. And then what will happen, that different layers have different velocity, because shear means like some velocity gradient. So depending on the position, so the particles will move. So this particle will move here, these two particles are moved. Now, due to the initial position, what will happen is these two particles will overlap, because they are very close to each other and so on. But if the particles are hard, this overlap is not allowed. So what will happen? The particles will get displaced randomly depending on this collision they are facing. Okay, so this is a simulation study basically. So it will undergo some collision. Now imagine what will happen if, so I had this system, I shear it at the beginning, and then I am bringing back to the initial state again. So then, since everything is over damped and there is no diffusion, everything will be reversible. So these particle which has not undergone any collision, it will come back to the initial position. So these configurations will be identical. But it is not true for these particles which have undergone collision, because they have been randomly displaced in between. So even if you bring it back to the initial point, they will not come back to this configuration again. Something has changed, right? So now in this paper, they studied many such particles. You have a collection of such particles, and they perform this experiment. What is the experiment? So you start with a configuration with lot of particles, and then you shear the particle up to certain strain amplitude and bring it back. Okay, and that we call, or rather, they called it as a cycle. Okay. So now what they are showing here is if any particle, it comes back to its initial position, then they represent the position with an open symbol, and other particles which have undergone collision, so their position are not reversible basically, they are displaced from the initial position, they are marked with this dark circle. So you see that for this certain strain value, gamma naught is equal to 3, there is a lot of particle undergone collision, some particles are completely reversible, and so on. So now what happens if you keep on applying such cycle? So this is after 1000 cycle, you see that number of some such irreversible particle, it has decreased. And if you continue, like you end up in a steady state where the number remains roughly constant, it fluctuates around some value, but it is less compared to the initial state. Now, I can do the same experiment for a lower amplitude, gamma naught is equal to 2, and I observe the same thing. So there some very interesting thing happens is, like I had a lot of irreversible particle, but as I apply these cycles, it is called some training. So this number of these irreversible particle is going down steadily, and I reach a state where everything is reversible. Okay, so then if you keep on doing this experiment, nothing will happen. Yes.
Is there a medium or the particle? Or
Yeah.
This shear is propagating through by the medium.
By the medium.
Oh, okay.
Yes.
And these are just suspended in the medium.
Suspended particle and neutrally buoyant.
Okay.
Buoyant and all.
In these plots, what is the reference state? Is it say before 2111 state, or is it the previous one? So when you say all of them come back with respect to what? I mean, is it the
with the initial configuration?
Starting one.
Starting one.
See.
Right. Yes.
No, starting one or is the previous cycle? Last
No,
cycle.
I mean this configuration.
Yeah.
Oh, each configuration.
Previous cycle, right?
Sorry, this is previous cycle, right. Oh, I thought that after 1, this will be the initial configuration, then after 2, it will be 2 to 1 actually, 1 to 2, that difference.
Always with respect to
Right, yes, yeah. Because if you consider with respect to the initial state, it is a optimized state, so there will be lot of like reorganization in that sense actually. Okay, so that's why greater than this number of cycles, nothing will get changed any further. Okay, and you reach something called an absorbing state. So where this fraction of active particles are nothing but these field particles, so they will drop and there is no further collision. But in other case, actually, like you reach a steady state where you have like roughly a similar number of particles undergoing collision. Okay, so and you can plot this fraction and you see as a function of strain amplitude, you see that beyond certain strain amplitude there is a sudden jump, right? And if you remember these beautiful talks by Andrea and Doug, what they showed that physics solves problem for you and which are complicated. So this is one such example, this self-organization. So given some volume fraction, this is I have forgotten, it is around 34 or something. And given a strain value for a complex configuration, if I ask you that what is the position of the particle where no collision will be there, it is a very hard problem to do. But now if you do this experiment, in this case this computer experiment, actually because of this interaction and this collision, the system will naturally evolve to this collisionless state. Okay, to give you this optimized configuration, it will depend on both the volume, area fraction and so on.
So after every cycle, you're waiting for some time to reach the equilibrium?
So because the equilibrium is reached instantly, because these are over damped, So if you remember Sanjeev's talk that if it is dynamics is overdamped, it will reach equilibrium instantly.
Okay.
Okay. Any other? Okay. Okay. So now, so how this self-organization is related to the memory formation? Okay. So here again, I have similar system. You can imagine like this is a paper by simulation study by Nathan Kaim and Sid Nagel. So what they are studying, that they are studying the property of the system. They are finding out like how many active particles are there after like this in the stroboscopic sense that they are bringing back in the initial configuration, and how many collisions are there in the system. But what they are doing, so first of all, so they are doing for different strain value, and you see that number of active particles are increasing as you go to higher strain, which is sort of trivial that if you apply a higher strain amplitude, the system is expected to undergo more and more collision. But now, next, what they have done, they have trained the system to a lower amplitude, like they are studying till 4. Now they are training the system up to a strain amplitude of 3. Okay, that means up to 3, they are repeatedly perturbing the system back and forth. And you see that this number of collision, which is reflected in the fraction of active particle, it is getting reduced up to 3, and then there is a sudden jump. Okay, there is a discontinuity. That means that I could reduce the collision within within the training strain, and then the collisions are increasing beyond. Strength of this discontinuity is becoming stronger and stronger, and finally I can reach a state after many cycles where up to this point there is no collision, but beyond that there is lot of collision again. Okay. So now, as if the system has developed a memory, it can remember that it has been trained up to certain amplitude, which is gamma naught is equal to 3. Okay, one can read out. If you show me this graph, I know that okay, the training has been applied till this up to this train value. Okay, so so this is for non-Brownian suspension, the same system I showed. So now same thing one can get for amorphous solids like glasses and all. So there you can again train the system. So so these two are equivalent description basically. So instead of number of active particle, what they are showing is the mean squared displacement after a full cycle. That means like see, if you deform the if you apply some shear and bring it back, then if the particle has displaced from its initial position, for those particles I'll get a finite mean squared displacement. But if the particle is completely reversible, the mean squared displacement will be 0. Okay, these two, like for this case also I could have plotted mean squared displacement. You will get pretty similar behavior. So now, so if you see that if I don't train the system, in this case the training is up to the strain amplitude of 0.06. So this amorphous solid is a complex material because this collision picture is not really valid because it has long range correlation. If you, because of elasticity, if you perturb some portion of the system, the perturbation will propagate long distance. So see, for training untrained sample, you get certain increase with strain amplitude, that mean squared displacement increases monotonically. This is almost this 0 cycle, this case. Now, as you train the system, you go to a state, you see that at that strain amplitude, which is the training strain amplitude, after 20 cycle or even 10 cycle, the mean squared displacement is almost 0. So that means at corresponding to the training strain, the particles, the system is completely reversible. Okay, so this is a complex system, and these two pictures are not really equivalent. There are some subtle difference that I'd like to point out, but I'll not be discussing much. Is like in these systems, something called ordering of state is valid, Whereas this system, ordering of state is violated. What is meant by that is, see, if I have trained this system up to strain amplitude 3, it is obvious that even if I go between 0 and 1 and after this training, there won't be any collision because they are not facing any collision up to strain 3. So if I confine my strain below that, there is no question of having collision. But that ordering of state is not valid here in the sense that, see, the mean square displacement is minimum for training strain, but below that actually there can be finite mean square displacement. So the trajectory is not completely reversible. The reversibility comes only corresponding to the training strain. So that has been observed in simulation. No, so here it returns to the same point again.
Okay.
But the trajectory here, like up to these, like if you plot the trajectories are identical. All trajectories are identical within these strains. So if you strain between 0 and 1, you get some trajectory.
Yeah.
0 and 2, same trajectory, but extended up to 2.
So this is like a ferromagnetic system in some sense, right? Like ferromagnetic, if you random ferromagnet, if you drive it with a magnetic field, and maybe that's like an anti-ferromagnetic where, or like the order in which this arrangement happens within that matters, but here the order doesn't matter probably, right?
Yeah, so one thing is like if you so what the simulation paper is reported, because these studies, like there is, I don't think no theory is there as
So
such.
so okay, so maybe in some other sense, like see, when you share the system, there are a lot of particles where displacement is happening, right? And then you have to rearrange those particles. So in this system, probably the way you rearrange this particle, that order doesn't matter. You will always end up in a one unique state,
Right.
right? But in this case,
No, so
now,
this system, it encodes the amplitude of maximum amplitude of training. So suppose you in whatever order you apply some training. So let's say I train with a strain of 2 or 3 or 1, such that like in maximally trained. So then it will be remembered the amplitude of maximum training amplitude of maximum strain.
like in this case, like for example, you stress to somewhere and there are 5 particles which moves, and now you have to find new position for these 5 particles, let's say, right?
Right.
Now, in which order you find the position for 5 particles? Let's say first you do 1, 2, 3 or 1, 3, 2, probably you end up in the same state. Right, but in that case,
So
probably
that is hard to tell, because see, same particle can also undergo multiple collision also. Right?
yes,
Because if you displace one particle, it is not guaranteed that maybe other particle can displace, and that's why like you need so many cycles to get trained fully.
Yeah.
Otherwise, it will get trained very quickly.
Okay. Yeah.
So,
Maybe we can.
you can.
Maybe.
Yes. Right.
Plastic events, but still those plastic events are exactly reversible when you are back to your gamma equal to 0. Hmm?
Now the order in which you are fitting them, because you can choose any order,
Hmm.
and the final state is independent of the order in which you are fitting. So there is some abelian property.
Ah.
But if you take an anti-ferromagnetic system,
This will matter. Hmm.
so that's why I was saying that, see, when you changing the system, the new state or state, there are 5 or 6 particles you can displace them.
Yeah.
Now, in which order you are displacing them, probably it doesn't matter. You probably end up in the same.
No, but in both the cases, actually, that order doesn't matter. When I say this ordering of state, I meant that if you have if you train a system for a strain amplitude of gamma, let's say that gamma n, so then the system is automatically trained for any strain which is let's say for that is less than gamma n. But now, here see, it is trained for 6% strain, 0.06, but it is not obvious that it will get trained for other. In this case, 3%, it has a small mean square displacement. But I think that landscape picture, but how you induce these collisions, that is completely same particle can undergo many, many collisions actually.
In this case, if it has a blob cycle, there will be no collision, right?
There won't be any collision.
There are no non-effect displacements here. So the ordering. So state is always unique. Between state is always unique.
Collisionless.
During one cycle.
Yes. Exactly. So that is exactly. So if you plot this energy versus strain or something, so then for a certain strain amplitude, suppose you go here. So you will always be confined to this, and then if you go to a higher strain, it will follow this kind of curve. But for amorphous case, what happens is suppose it is reversible, but this reversibility is kind of complicated. So this first and this point can be reversible after full cycle though. Let's say this point is reversible, but in between that reversibility is not there. You can get various values for same strain. Yeah, this is loop reversibility because of that. Maybe you can discuss later. Okay. So these are simulation studies, and experiments also these are verified. So these are PMMA particles in a solvent that is density and index matched. So there also you see this thing if you train the system, you go to this collisionless state, and then suddenly this mean square displacement increases. So this is mean square displacement normalized by the particle diameter square. Okay, and you can encode memories in different strain amplitude and so on. So this same has been shown also for amorphous solid by this Srimoy, Rajesh, Sud and so on. So this is on a 2D bubble wrapped system. It is again an amorphous solid, not like this kind of system because it has long range correlation. So there also you train the system and you show that mean square displacement shows a dip very close to zero actually given the noise floor for training amplitude. Okay, but in between the mean square displacement is finite. So this has been also observed experimentally. Okay, so everything is good. So now if you remember the question I initially started with, that can we encode memory and change the properties of material? So now what happens for these two experimental systems, let's say that what happens to the mechanical property. So if you encode the memory, this is exactly the system, that PMMA particle system. So if you draw a stress versus strain curve, you get this black curve. Okay, if you plot stress versus strain, you get this black curve, and actually corresponding to some training amplitude, maybe 1.4 or something. So there is a small kink here. So if you take a derivative of this curve, physically it measures the differential shear modulus. So you get a kink corresponding to the training amplitude. But if you look at the response, actually it is a very tiny fluctuation, right? It is just a very small shift. So mechanical property doesn't change significantly. Similarly, if you plot the stress versus strain for the bubble wrapped system, the training amplitude is 0.071, and there you see a very tiny kink. So virtually that bulk mechanical property, there is no change in both the cases, both amorphous solid and. So now we ask that is it possible to tune the mechanical properties of a system by encoding a memory? That has not been addressed. Yes.
Yeah. But when you do oscillatories here and reach the steady state, then you have annealed the system, right? You're annealing it significantly. So the mechanical property do change.
No, but see, you anneal the system, but when you do a readout measurement, so this is the readout measurement actually. So readout, so what I am telling that this tau versus gamma, when you plot, the property of the system, it is true that from annealed state, it is independent of the memory. So you do some perturbation, some cyclic shear, the overall mechanical property will change. But the question is, since you have encoded memory of certain strain amplitude, whether that mechanical property is sensitive to that strain amplitude, because mean square displacement show a very sharp dip at that point. So corresponding to that, is there any change in the mechanical property? In that sense. Yeah, but you are absolutely right. Corresponding to the initial state of the system, the property will change, but that will change for any protocol basically.
Any protocol, yeah.
Right. Okay. So now, so we studied this system. These are cornstarch particles, and these particles are amorphous particles having diameter, average diameter of around 15 micron. So now, if you put these particles in a hydrophilic solvent, because these particles are hydrophilic because of OH groups on the surface. So if you put them in a hydrophilic solvent, they are well dispersed. Okay, hydrophilic solvents like water and glycerol. And if you pack more and more particle, you finally can form an amorphous solid at quite a high volume fraction of 56%. Okay. Now, what happens is if you put these particles in a hydrophobic solvent like oil, okay, so these particles, they do not like the solvent, so they try to form these clusters, okay, and you get these fractal clusters, and one consequence is you can generate the solid-like state at very low particle volume fraction, much lower than 5J, okay. And we see, like, we fluorescently label this particle, and you can see this clustered state, and you can compare with this well dispersed state. So this clustered state, you can see that. So these are quite different from this well dispersed state. And another thing, you can measure the shear modulus as a function of volume fraction. You see that for this system with fractal clusters, it develops shear modulus at very low volume, quite low volume fraction. Whereas if you put the particles in a hydrophilic solvent where they are well dispersed, to develop same kind of elasticity, you have to go to very high volume fraction. Okay. So now we started with this system, and this is our experiment. So what we do, again, we apply this training. So we are training the system back and forth by some strain amplitude gamma t, and we typically apply 300 cycles, and then we note down the response as a function of number of cycles. So two things you notice, that this is the stress response. So two things you notice, that the stress, actually the peak stress slowly decrease, and also if you look at these curves carefully, you see that there is some slow evolution of the nature of the waveform. Whereas if you look towards the end, after like let's say from 295 cycles and all, so you see that the peak stress has decreased significantly, and it settles down to almost a constant waveform. Okay, and you can question. So you can plot the peak stress, and for different training strain and all, you pretty much get the similar evolution. And you can also plot the stress versus strain curve for n, where n is number of training cycle. You can see that for no training, it is a very plastic, this Lysagius plots actually, this very plastic signature. And then as you train the system is getting annealed, what Sarojit was pointing out. But not only the property, the values are changing, but actually that's why I'm plotting this normalized stress in the y-axis. So you see that the nature of the plot is changed also, because this is almost like stress and strain is almost linear and it has plasticity, but here you get some strain stiffening response where the slope of stress versus strain is low for small gamma, but at high gamma it picks up. It becomes highly nonlinear. Okay, so now suppose the question is like, if we train the system, is there any effect on the mechanical property? So we train the system for 300 cycle with a strain amplitude of 2%, 0.02, and then take a readout and we compare the system. We take another sample and after loading we don't do anything, we directly take a readout. Is there a difference? So this is the comparison. You can see that for untrained sample, this black curve, like you get this plastic curve that I told you before, whereas for this red guy, like corresponding to the that corresponds to the readout for the trained sample, you get that there is a sudden, like there is a stress strain curve show very small slope initially, but there is a sudden rise in the slope and you get this curve. Now, if you take a derivative, both this curve, only this upward side, so you see a clear difference that this red curve actually it gives very pronounced peak. Okay, so that means you have very strong differential shear modulus corresponding to the training strain amplitude, which is 0.02. 0.02 you get a very strong peak, and you can compare these peaks for the earlier study and like this peak divided by the baseline. You'll see that they were of the same order, but here we get huge enhancement. So actually the mechanical property of the system has significantly changed. Now what we can do? We can do this for same system. We can do this for various training amplitude, like this 2%, 4%, 7%, and so on. You see that you get very strong response exactly at the training strain, and the response becomes gradually weaker and particularly becomes very weak beyond 10% strain. 10% actually, I don't have the data here, but this corresponds to the yield strain of the system actually. So beyond this, actually the system is pretty much fluidized. Okay, so here you can get some signature, but those are very minor. Now I'd like to point out that, see, this memory formation, if you realize, it is beyond the linear and non-linear viscoelasticity of a material. Like you can have for a given material, you can have a linear rheological behavior, you can have a non-linear rheological behavior, but here that is beyond that, because the material response now I am controlling by applying a training. It is nothing in I am not changing the material, but they are showing, yeah.
Does this really have a linear regime?
It doesn't. For this particular system, it doesn't have.
I suppose would not.
Yes, I mean, at least it is supposed to have some linear response regime, but what we observed up to certain strain that we could go to, it is starting from the beginning very non-linear. We could have gone to even lower strain because linear response should be there, but they are like, we are not sure about the resolution of the instrument because the data becomes noisy, then it's hard to interpret. Yeah, but in general, I am telling that because some of the systems, like for example, bubble raft and all, they have a linear response regime, clearly that you see. So, yeah. Right. Fluctuations in the data. So, because see, I'll show you. In this case also, here it is not negative, but you can see that these small fluctuations, which are very small, but actually their x-axis is also very small. So sometimes those fluctuations can give close to the baseline these negative values. Yeah, particularly when they are small, you can get frequently. Yeah. Yeah, that's a good point actually. So athermal as such, if you are talking about particle size wise, it is not a requirement, but you know, like if the system is performing Brownian motion, then whatever structure you create, it will melt away. But colloidal gel is a different example because this is a arrested system, right? Same as colloidal glass. So those systems you can encode the memory, but for a Brownian system also, I'm not telling, although we haven't done the experiment, the memory encoding is possible because it is related to structure. But due to Brownian motion, the structure, the system will equilibrate. Then the memory signature will not be there.
Okay, got it.
Okay. Another question? Okay. Okay, so we can also encode multiple memories. I told you that only single memory, but you can train the system suitably. It is little non-trivial actually how to do this, but you can see like peaks at 2 different training amplitude and so on. Okay. So to get some more insight, what we did, we set up some in situ imaging, in situ boundary imaging, because particles are opaque. So we have this shearing geometry, and the sample is here confined between these 2 plates, and then we shine light and we record the boundary image with the camera. You can see like you get typically these kind of image. Some particles are protruding out. Yes.
So when you choose your training strains,
Yes.
okay, do you keep the yield strain in mind? Because that's where you think that.
Yeah, that is what we learned actually, because initially some of the cases like that is something we don't really understand very well, because in case of amorphous solid like bubble raft, and we have some system that Maitri is studying also. So they also claimed that close to the yield strain where some rearrangements are allowed, there actually you can encode strongest memory. But for our case, we found that actually like the memory signature gradually decrease. We found that you encode strong memory for small amplitude well below the yield stress, and then they gradually decrease, but after yield stress they are completely gone. So there is nothing special as far as
multiple memories.
right, but both are like below yield stress actually, yield strain rather in this case. So this because yield strain is around 10% or slightly more. So I showed you for 2 and 4, but typically we try to keep it below 10.
Starts flowing, there's no.
There is no memory, which is expected actually. If you fluidize the system, all the structures will be destroyed. Any other question? Okay. So now what we can do that, so these in this case, although the picture is little misleading, you can do both, but here we actually move the bottom plate of the rheometer. Now how we analyze this image, so we take this bright speckle on the plate, so this is basically the bottom plate, and we take another region, another bright speckle inside the sample. Okay, and we observe their trajectory as a function of time. So basically it will how they are moving basically along this line, the motion is horizontal. So for point A, you get this kind of motion. So these are kymograph analysis basically. The intensity will tell you how the motion takes place. So this is supposed to be your input. So we verified that the input is remaining robust. You don't expect, you don't allow the input to drift around. Then all the memory interpretation will be total nonsense. Okay, so this remains robust. What happens if we do the same exercise for a point inside? So you see that actually those points, their motion, it is evolving actually slowly, and after many cycles it settles down to this kind of waveform. And now we can also do that corresponding to the readout experiment. Readout is basically you apply some training and then you overshoot it with same rate and everything is identical, but you cross this point. So now what we observe, if you look at these curves carefully, what is the response of point B? So A is increasing smoothly and then going in the other direction as you shear the plate back and forth. So here you see that these particles, it is initially following the same motion, but after that like it slows down. That means there is a kind of slippage somewhere between B and A. So actually we understand that there is a shear band formation because these are adhesive, attractive system or adhesive systems, shear bands are common. And then interestingly, during readout, as soon as you cross this strain amplitude, there is a sudden jump. here, that as if like there is a slippage developing, but that slippage, it is kind of a training dependent slippage. As soon as the readout crosses this value, you see that again the coupling build up. And now, although I am not showing the data, that point B can be chosen anywhere, like except for very close to this plate. So you can choose from here till here. So anywhere like this signature is preserved because you have a shear band formation, a very narrow shear band formation close to the plates. So then it tells you that as you cross this point, there is a sudden increase in velocity of a large portion of the sample. So that explains that why you have a like weak stress up to certain strain value, and if you cross that training strain, you have sudden increase of stress actually. Okay. So although this is what we find, and that can explain our observation that stress increases beyond this as you cross the training strain. So what is the microscopic picture? This one, it is quite close actually, but it may not be same. Yeah, we haven't checked that precisely. Yeah. Okay. So now we came across a paper, exactly what Vaibhav was pointing out, this colloidal gel, although they don't talk about memory. So they are studying something like cyclic softening. Okay, so what they are studying, that if you take a colloidal gel and you apply this repeated perturbation, what happens to the response? Okay, so two things you notice, that for small strain, actually the response is much steeper because stress versus strain, that slope gives you the elastic modulus. The slope is decreasing with increasing strain, but what they are really interested in, you choose a particular strain and you repeat these cycles. So then you see that the system actually slowly evolves, the stress value actually becomes weaker and weaker. So this top portion is this one is the first cycle, then second cycle, and so on. So the system cyclically becoming weaker and weaker. So it is nanoparticles, so it is hard to see. So they did some simulation, and the gel typically has this porous structure. What they found, and you have these strands in the gel. Okay, so you can imagine like these as some strands. So what they found is, as you do the cyclic deformation, the strands are getting plastically deformed basically. That means the strand length, it is irreversibly increasing as you, so it is becoming loose in some sense. Okay, so this is strand plasticity. So now the question, so another interesting thing is like they also observed this strength stiffening. Okay, so after training we also observed this strength stiffening response. So we are thinking, can you imagine such a picture? Because see, unfortunately we cannot do a typical volume fraction we probed experimentally. It is 40%, 30%. There we found it is very hard to visualize the sample optically. It is so dense. But if we go to a lower volume fraction, where the force measurement is very weak, so we couldn't really correlate these two yet. So you can also see like a similar kind of strand in the strength stiffening regime. Like you can see that this connected structure, porous gel kind of network. So now, given this picture, how do we understand memory in this system? So imagine that one such system spanning strand for input strain equal to 0. Now, as I am straining the system, the strand is getting stretched gradually and getting more and more stretched. This is up to training strain, and I am getting some stress versus strain response. So this strain stiffening is very reminiscent of stretching of this elongated structure that we also observe in biopolymers, semi-flexible polymers. Okay. So now imagine that after many cycles, so this not even in the next cycle only. So let's say many cycles. So this stretching has plastically defined the strand. Okay, so now the strand has become very loose. So if you come back to the initial point, Actually, now this is your configuration. The strand, because it has got stretched, like similar to gel plasticity. And then what happens is, if you deform it slightly, you cannot stretch it out fully. And then to stretch it out, you have to even up to maximum strain, it is not fully stretched. So what is the consequence? The consequence is the following, that you get very weak response, because as if you don't stretch the strand, you will not have significant stress response. That is what we observe, because if you look at this curve, so the slope is very, very small in the strain stiffening regime. But now, can we explain the memory? So now, if you go beyond this training strain that we are doing by readout, the strand is loose up to this point. But if you go slightly more to slightly more strain, the strand can again stretch and engage. And then you can have a strong response. So this change in slope, if you take a derivative, actually it will give you a peak here. So that is a physical picture one can consider. Now, what is the essential ingredient of this picture? Because we couldn't really test it, because what I said, that it is hard to do this experiment for high concentration. So the main ingredient for this picture is, yeah.
This is resulting in the strand becoming loose. So this means that you are inadvertently encoding memory in this direction also, because this will respond in the same way in a tensile stress.
In a tensile stress.
Yeah. So instead of shearing, now you do the tensile stress.
Yes.
You get a similar response.
Right.
So you're encoding a separate memory there also, in some sense.
Right. But here we are doing only shear. But if you do this tensile stretching and this one, you can also encode a memory. Yeah, but here we are not doing any tensile stretching.
No, suppose you train using shearing. Now you read out using tensile.
That can also reflect. Yes, that's a good point. Actually, we looked at it briefly, but only point thing is like, if the I'll come to that point. If your adhesive interaction is very strong in gel, it is much stronger. Actually, that's why like even 18%, 17% volume fraction, you get solid-like response. But our case, it is not such a strong adhesion. So then it comes. Like the sensitivity of the instrument, because these rheometers are typically more sensitive for shear compared to the normal stress, but that is possible. That's a good point.
Sayantan,
Yeah.
so you said that, okay, it's difficult to verify experimentally, but it will be easy to do a simulation of this physical picture, right? And then
Yes.
see whether you get the same behavior or not.
Right. For granular thing, it will be very nice, because
also,
gel, they studied by simulation only.
No, I was not even thinking about that one. This band, elastic
Right,
band,
right.
and then when you pull it after some time, it
Yes.
uses. So you can write down some simple model and then simulate that model, right? I guess.
Okay, maybe.
I mean, that's the same physical picture what you have.
Yes, just based on single strand.
Yeah. So, but now you can put multiple strand at some random position and connect to the top plate.
Yes. That's yeah. Because we can talk actually some, yeah. That will be a good. Yeah. So now, if you realize the essential ingredient, I have to go a little fast. The is for the validity of this picture is the adhesive interaction between the particle. Because see, if you have dry grains, then you don't have any tensile response, right? So then adhesion is essential. So if this picture is true, what happens if we kill the adhesive interaction in the system? So we did exactly that. So you can put surfactant, and the particle gets coated with surfactant, and you can kill the adhesive interaction. So you had this connected structure initially. So with increasing surfactant concentration, you can break the structure and finally go to a well dispersed case where no adhesion is present. And surely enough, like you see, like for any value of strain, your peak value of k, that remember the derivative peak, that was our readout for memory, that actually decrease and vanishes for very small amount of surfactant, even 0.3%, 0.5%, the memory signature is completely gone. So looks like we are on right track, because it is validating. So now in last 5 minutes, I'll just go over quickly to some new data that we don't really understand, but yeah. So now what about the stability of the memory? Okay. the question is, how does encoding a second memory affect the existing memory? So I told you that, okay, so till now what we are doing, we are training the system repeatedly, then we are applying a readout, okay, and we are reading out this value. So now these are the readout, stress versus strain for this readout curve. You can see that for the first readout cycle, you can actually get this discontinuity exactly at the training amplitude, which is in this case 4%. Okay, so if you take a derivative, you get a peak here. But now what happens if I continue to apply this readout? So surprisingly, we found that even if you go to the next cycle, the memory signature is completely gone. See this green curve and blue curve, second and third cycle. So what we conclude that applying a larger amplitude catastrophically destroys the encoded training amplitude within just one cycle. What we go other way around? So first we train with a larger amplitude and then we apply a smaller training amplitude and do a readout. So there, in this case, this training amplitude is 6%, this is higher, and this sigma n is the n number of smaller amplitude, which is the 4% strain. So you see that after n is equal to 10, after applying 10 cycle, still some signature is there for the around 6%. So this memory still survives, and you might argue that there is no memory at 4%, but if you zoom onto it, you can see that very small jump. Actually, in some cases, like I'll tell you how to enhance this small memory and so on. So this actually, if you apply a smaller training amplitude, the larger memory survives. Okay, so now what we did, we studied that again from the magnitude of k peak at 6%, we asked the question that 6% what is the memory as a function of this number of this smaller strain amplitude, where the amplitude is kept constant at 4%. So this is the green curve. You can see that initially the k value was quite high and then it slowly decays, and within 20 cycle, like it is almost zero. So we can tell that even smaller cycle, smaller amplitude can destroy the larger memory after sufficient number of cycle. And also, like if you plot this discontinuity corresponding to this smaller amplitude, it increases and finally saturates. Okay. But now this is the surprise actually. So till now what we are doing, we are reading out this peak value at corresponding to this training amplitude of 6%, same data. So, and we concluded that, okay, so this is, the memory is going away. Surely this k value is almost zero for 6% after so many cycles. But now it was surprising that what we found, that this memory, this peak was not going away. Actually, it was shifting to some other value. You see, like this is in between 6 and 4, like close to 5% or something. This is very surprising in the light that till now, whatever studies we have come across, be it non-Brownian suspension, amorphous solid, everywhere what you observe, you train, you can have multiple memory, but those memories exactly you get at the location of where you train the system. But now this is telling that I have not done any training at 5%, but the memory is getting shifted to 5% for some intermediate value. Okay, and you see like this peak position is actually shifting, and we tried a bunch of input like two amplitude basically, training and gamma in 8%, 1%, 8 and 5%, 6, 4, many such combination, and looks like it is a robust trend that in all cases the position of the memory gets shifted with increasing number of training cycles. Okay. Now this is the thing I was mentioning, that now we have, like the previous experiment was for 1 second inverse strain. Yeah.
So is there any reason why the height, your differential modulus value, that is non-monotonic with
Yes.
training cycle?
So that is something we don't understand actually. So we initially expected that it will go down monotonically. So most of the cases it does happen, but in between, for example, here this is around 9,000, then 10,000, then it decreases. So we found that quite often actually this it is quite fluctuating. Whereas this position of the shifting of the memory is very, very smooth, but the magnitude is not so. So that is some observation, but we don't know like what is the reason.
Sayantan here. So this peak shifting is when you are reading multiple times.
Right. I mean, I'll so call our readout is same. So now actually I am applying smaller perturbation multiple times actually before readout.
So that is shifting your
that is shifting the memory
to the in between somewhere.
in between. Yes. And now this was 1 second inverse, and so how much time do I have?
2 minutes.
Oh, 5 minutes. Okay, that's enough. So now, if you increase the strain rate slightly from 0.01 second inverse to 2 second inverse, and so you see like not only this smaller memory becomes very strong, this shifting is very, very dramatic actually. And 4% like 0.04 second inverse, you can see that shifting is so dramatic that these two memory merge very, very quickly within maybe 40 cycles. Okay, so this is the strain rate dependence, that how quickly. So higher shear rate is more effective in shifting the memory. So with that, I'll conclude. So I told you that about encoding mechanical memories in adhesive granular gels. One of the salient feature is like mechanical properties of the system can be tuned by encoding this memory. That has never been shown, at least as far as we know. Then multiple memories can also be encoded. So these are something we'd like to understand. We are calling that intermediate memory is phantom memory because it is appearing.
Can you go back to the previous slide, please? Here you're showing the data where you have trained this system for 60 cycles, the second training, basically, the readout cycles.
No, these are not readout actually, because there are 3 levels now. Like one is training, one is molar perturbation, and readout is a single one. So as a function of that second smaller perturbation, number of cycles of that.
What if this smaller perturbations is more than 60 cycles? Because you have shown this shift only in 0.04 to 0.06. So does it go even below that? Or
no, because this molar perturbation is 4%. So the memory is already there. So that memory typically saturates at that point. If you keep on applying 4%, so and then do a readout, like the memory will be pretty, it might get little stronger or something, but it will not shift around any further. Your shifting always happens in the intermediate regime. Okay, so 6 to 4. This yes, Mahesh, you had.
This slightly differently. When this whole memory business was proposed by Sid and Nathan and Joey and all, he gave this example of studies from charge density waves from some 2-3 decades before, where the response was it was after many cycles of training, it was almost anticipating that it will receive the spike, and even before the spike arrived, it gave the response.
Yes.
It's almost sounding like a causality violation.
Yeah.
So if you say that I expect the response to arise at 6% strain, but if it is showing up at 5% or 4.5% and so on, that is analogous to anticipating the response in advance in the charge density context. So nobody may have reported this in the amorphous solids space, but I feel there may be an analogy with the charge density case. Okay, I think you should. Yeah. I'm not the expert on this.
Right. That's an interesting perspective. So only thing I'm thinking that it is this just a part of different cycles. So time-wise, they are not very defined, but we can talk about that actually. Yeah. Thanks. Okay. So
questions.
Okay, so I have just 2 last points. Anyway, you can ask questions, no problem. So some of my students, they are studying other type of memory, like memory of waiting time, Kovacs effect in glassy material. Maitri and Abhishek were here. And also in strong shear thickening and shear jammed system, apparently shows very interesting memory effect that we are studying. So this experiment also we are discussing with Rituparna, who is a postdoc in New Chicago, and this part is with Sachidanand, who is here, and also another postdoc at Georgetown, Vinuta. Actually, we are trying to do some simulation, who is an expert of shear jamming, and so all the experiments and analysis are done by my grad student Shavanti, who is here, and Jatindran for SEM imaging. These are my current lab members, and I thank RRI and SERB for financial support. And these are based on these two publications that came last year. And thanks for your attention. More questions?
Any more questions?
Trying to erase eventually at long time or a large number of strain cycle the large memory, and the rate at which you are doing will determine how many cycles that you need. This is exactly the point, right? Yeah. Okay.
Looks like that, and the rate is not very different. Actually, see, we went from 0.1 second inverse to 0.4. Looks like that is a very sensitive parameter. We were not looking for rate dependence, but that seems to be. I don't know, like why we did that experiment.
But I don't know. We recently studied multi-directional shearing, and we see very interesting things, including multiple absorbing states. Is it possible to do multi-directional shear? Directional shear.
Not
so in one way.
Yeah, in rheometer it is difficult, but you can imagine, like, if you design some stage which can be independently controlled, it is possible actually. Because you told me before, but it is
we see if you do let's say XY versus YZ shear, you get to steady state which has two absorbing states, and if you do three direction, then you get three absorbing states, and करूँगा बाद में.
Yeah, but only thing is, like, I don't know, like, how independent those drives are. But if it is just matter of direction, probably that will lower. The best thing is, like, if you independently design a stage that can be controlled independently than rheometer, like, I think that. Yeah. Sorry. Keep you waiting.
So let's thank Professor Sayantan for his wonderful talk.